Your laptop is doing nothing right now. But on a server somewhere, a single Nginx process is holding 100,000 open TCP connections. Its CPU usage? 5%. One thread, not one thread per connection. One thread total. So how does it know which sockets have data without checking every single one in a loop? If you tried to handle 10,000 connections with the obvious approach, one thread per socket, your machine would melt. The memory alone would eat tens of gigabytes, so nobody does it that way. Today we're going to dissect the Linux kernel feature that makes massive concurrency possible on a single thread. It's called epoll. It's the foundation of every modern high-performance server. And once you understand it, you can read the source code of Nginx, Redis, and Node.js with new eyes. The simplest way to handle many connections is the obvious one. Spawn a thread for each. Each thread blocks on read until its socket has data, then handles it. Beautiful, easy to write. It works until it doesn't. By default, every thread on Linux gets about 8 megabytes of stack memory. 8 megabytes per thread. At 10,000 connections, that's 80 gigabytes of memory burned just on stacks, before you've handled a single byte of actual work. And memory isn't even the worst part. The kernel scheduler now has 10,000 things to switch between. Context switches start dominating your CPU time. Cache lines get thrown away constantly. This problem has a name. It's called the C10K problem, 10,000 concurrent connections on one machine. The naive approach hits a wall hard. We need a fundamentally different shape of solution. Linux has had I/O multiplexing for a long time. The original syscalls are select and poll. The idea is simple. You give them an array of file descriptors you want to watch. They block until at least one is ready. Then they return the ones that are. Sounds great, so why isn't this enough? The problem is what happens inside the kernel. On every single call to select or poll, the kernel walks your entire array, checking each socket's readiness flag. The cost grows linearly with the number of file descriptors you're watching. Worse, the array itself gets copied between user space and kernel space every time you call. 10,000 sockets means 10,000 checks per call, and you're calling this in a hot loop. Select doesn't scale by design. The fundamental shape of its API guarantees the cost. Here's the insight that makes epoll fast. The old syscalls treat the kernel like a search engine. Every call you ask, "Is anyone ready? Please check all my sockets again." Epoll treats the kernel like a notification service. You tell the kernel once, "Here are the file descriptors I care about. Here's what I want to know about each one." The kernel keeps that list. It maintains it. When a socket becomes ready, the kernel itself updates an internal ready list. Your code only finds out about the things that actually changed. The cost stops scaling with how many file descriptors you have. It starts scaling with how many are actually doing something at that moment. Don't poll the kernel, subscribe to it. That's the whole idea behind epoll. Epoll is just 3 syscalls. First, epoll create one. The kernel allocates an epoll instance and gives you back a file descriptor that points at it. Think of this as opening a notification box. Second, epoll CTL. CTL stands for control. You call this once per socket with the add operation telling the kernel, "Add this file descriptor to my epoll instance, and here are the events I care about. Read ready, write ready, hang up." Third, epoll wait. This is the one your loop calls over and over. It blocks until at least one of your registered file descriptors is ready, and then hands you back an array describing exactly which ones became ready and what kind of event happened on each. That's it. Create the box, register interest, wait for notifications, 3 calls. That's the whole user-facing API. Inside the kernel, an epoll instance is 2 data structures. First, the interest list. It's a red-black tree keyed by file descriptor. Every FD you've registered lives as a node in this tree. Lookups are logarithmic. The tree can hold 100,000 sockets and still find any one of them in microseconds. Second, the ready list. It's a doubly linked list of file descriptors that have just become ready, but haven't been delivered to user space yet. Now here's the magic. When you register a socket, the kernel installs a tiny callback on it. When the network stack delivers data to that socket, the callback fires. It finds the FD in the tree and appends an entry to the ready list. Epoll wait just returns whatever's currently in the ready list. The user's call doesn't scan anything. The kernel did the work asynchronously, the instant the data arrived. Epoll has two modes, and this is where most of the bugs come from. The default is level triggered. As long as a socket has data ready to read, every call to epoll wait will keep telling you about it. Easy to use, hard to get wrong. Edge triggered is the alternative. It only tells you about a change of state. The moment a socket goes from empty to having data, you get exactly one notification. After that, epoll stays silent until something new happens. The implication is subtle and important. In edge-triggered mode, you must read from the socket in a loop until it returns EAGAIN, meaning the buffer is fully drained. If you don't, you'll deadlock, waiting for a notification that already happened. Edge-triggered is faster, fewer wake-ups, but you only use it when you're certain you can handle the bookkeeping correctly. Here's the pattern that powers basically every modern server. A single thread, an infinite loop. At the top of the loop, you call epoll wait. The kernel hands you back the events that have happened since you last asked. You walk through that array. For each event, you dispatch on the type. If the event is on your listening socket, that means a new connection has arrived. You accept it and register the new socket with epoll. If the event is on an existing connected socket, you read whatever data is available. If a socket signals that it's writable again, you drain whatever pending output you have into it. Then you go back to the top and call epoll wait again. One thread, no locks, no context switches between connections. The CPU works on whatever needs work the moment it needs work and sleeps the rest of the time. This pattern isn't theoretical, and it isn't rare. Nginx is built on it, Redis is built on it, Node.js's libuv runtime is built on it, HA proxy, Envoy, the Go runtime's network polar, all the same idea. The languages differ, the user-facing APIs differ, but underneath the architecture is identical. A single OS thread, an epoll instance, an event loop driven by epoll wait. The reason these systems can each handle tens or hundreds of thousands of concurrent connections per process, using a tiny fraction of the CPU, is that, at the bottom of every one of them, they're leaning on this one Linux feature. Once you can read epoll's API, you've gained the ability to read the source code of an entire generation of high-performance software. They're all variations on the same theme. Epoll is brilliant, but it isn't the end of the road. Every epoll wait is still a syscall. Every read is still a syscall. Every write is still a syscall. At 1 million events per second, the cost of crossing the user kernel boundary itself starts to dominate. That's where the newer interface, epoll, comes in. It takes the same insight one step further. Instead of telling the kernel about operations through syscalls, you and the kernel share two ring buffers in memory. One for submitting operations, one for collecting their results. The boundary is still there, but you cross it without trapping into the kernel for every single event. The lesson, though, hasn't changed since 2002. Don't poll. Let the kernel hold the state. Wake up only when there's real work to do.